All right, so today we're going to cover chapter 17, which is all about aqueous ionic equilibrium. So we're going to apply what we learned in the previous chapters 15 and 16, regarding this concept into aqueous solutions. And this would involve ionic compounds that are dissolved in water. So here's an outline of what we're going to cover today. Regarding this chapter, we're going to learn what buffers are. Right? We're going to define different types of buffers. We're gonna learn how to calculate the pH of different buffer solutions using the Henderson-Hasselbalch equation, which is basically a shortcut. And then we're also going to learn the concept of titrations and how we can determine the pH after titrating an acid with a base or titrating a base with an acid. And we're also going to cover monoprotic versus polyprotic acids. We're going to learn about pH indicators, solubility equilibria, and precipitation reactions. So I'd like to start off this chapter by introducing this compound called ethylene glycol. And ethylene glycol is actually a type of alcohol. And alcohols are a type of organic compounds. So a lot of these alcohols, so ethylene glycol again is basically a type of alcohol because it contains what they call hydroxyl groups. All right, so remember that carboxylic acids, they have what they call carboxyl groups, which is basically COOH, right? And for alcohols, we have OH groups, which are called hydroxyl groups, right? So these are signature groups that make them examples of alcohol. So for example, if you look at methanol, right, methanol has this general formula, CH3OH, right? Ethanol, same thing, CH3, CH2OH. And a lot of alcohols, they end in OL, right? So we have methanol, ethanol, propanol, and so on and so forth. So they all end in OL, alcohols. Okay. Similarly, ethylene glycol ends in OL, and so this is how you name alcohols. So you'll learn all of that in chapter 21, which is organic chemistry. So ethylene glycol is a major component of antifreeze, and antifreeze, when consumed accidentally, can be fatal. All right. The reason why is because ethylene glycol, when consumed, right, when ingested by accident, they get metabolized in the liver. Okay, and they break down into glycolic acid and then eventually into oxalic acid. And glycolic acid and oxalic acid are both examples of carboxylic acids. And sometimes you don't even know that you've actually accidentally ingested ethylene glycol because it tastes sweet, right? It basically tastes like candy. Ethylene glycol, because it's an alcohol, has the same effect as any other alcohol, right? So it'll make you feel drunk, tipsy, dizzy, and so on and so forth. And so at high enough concentration, the glycolic acid could cause the blood pH to drop, to decrease, basically, right? So glycolic acid overwhelms the buffering ability of your blood, which causes the pH to decrease. All right, and so when that happens, your body undergoes this condition called acidosis, in which the low blood pH compromises the hemoglobin's ability to carry oxygen molecules. And so here's the chemical reaction equation showing you the binding competition between oxygen and the acid, right? So you have oxygen molecule here and the hemoglobin that's binding to the hydrogen ion, right? So the higher the concentration of the acid, again, this is in equilibrium, based on Le Chatelier's principle, the higher the concentration of the acid will result in shifting of the equilibrium to the left, which means that it favors the formation of this hemoglobin hydrogen complex, right? So instead of binding to the oxygen, you're favoring the binding of the hemoglobin with the acid. And so that basically results in not binding oxygen. So if the hemoglobin is not binding to the oxygen molecule, then you're not getting any oxygen in your body. Oxygen deficient muscles will not receive the oxygen that they need, and this could lead into coma and even death if not treated properly. And one way to treat this condition is to give the patient alcohol, right? The reason why is because alcohol has a greater binding affinity for the enzyme that catalyzes the metabolism of ethylene glycol. So this enzyme is called aldehyde dehydrogenase. All right, so because of this higher affinity for the alcohol, the enzyme will basically ignore the ethylene glycol because it has higher affinity for the alcohol, right? So ethylene glycol gets bypassed, right? It bypasses the liver and the kidneys, and then it gets excreted out of the body through the urine. All right, so the next topic here is buffers. We're going to define what buffers are and how to calculate their pH. So by definition, a buffer solution is any solution that contains a combination of an acid and a base, right? And it has the ability to resist the changes in the pH by neutralizing the added acid or added base. And there's actually several different types of buffer solutions. An acidic buffer, okay, is a solution that contains a weak acid and its conjugate base. So that's what makes an acidic buffer. We can also have a basic buffer, right? A basic buffer would be a buffer solution that has a pH greater than 7. And a basic buffer contains a weak base and its conjugate acid. All right, so blood, for example, has the ability to resist pH change because it contains buffer, right? Blood has a mixture of acetic acid, which is a weak acid, and its conjugate base, okay, which is the bicarbonate ion. All right, so how do we make an acidic buffer solution? Again, an acidic buffer solution is a solution that contains a weak acid and its conjugate base, right? It has a pH below 7. So an example of a buffer solution is a combination of acetic acid and its conjugate base, a salt of its conjugate base, which is sodium acetate. Remember that acetate here, C2H3O2 minus, is the conjugate base of acetic acid. All right, so in this buffer solution, we have the acetate ion and the acetic acid, and of course water and sodium ion. All right, and so if you were to add a strong base into this buffer solution that contains a weak acid and the conjugate base, the strong base, let's say sodium hydroxide, right, will react with the acid component of the buffer, okay? And the acid component is acetic acid. And so the hydroxide ion coming from the sodium hydroxide will react with the hydrogen, right, coming from the acid. And so this hydrogen and the hydroxide will form water. And then we have the sodium and the acetate ion forming sodium acetate. All right, so this is how buffer solutions, or at least acidic buffer solutions, neutralize added base. if a strong acid is added into the buffer, then the conjugate base will neutralize this acid that was added, right? So for example, if we added hydrochloric acid, which is a strong acid, into the buffer solution, then the conjugate base component of the buffer solution will react with the acid. So you can see that this hydrogen right here, right, will react with the base, the conjugate base. And when that happens, you're basically regenerating the acid, right? Acetic acid, right here. So you're regenerating that, and the chlorine or chloride ion and the sodium ion will react to form the sodium chloride. All right, but the entire the main goal here is to understand that the added acid will react with the conjugate base present in the buffer solution. And the added base, strong base, will react with the acid component in the buffer solution. And that's how they neutralize acids and bases. All right, so I'd like to talk about common ion effect, right? So if you have a weak acid solution, okay, so let's say again we have acetic acid here. Okay, we have acetic acid ionized in water, and this forms hydronium ion and conjugate base, right? So if we have this weak acid solution and you added a salt, right, containing the conjugate base, let's say this one right here. If you added a salt, let's say sodium acetate, right, C2H3O2 minus. Okay. So this acetate right here is now considered the common ion, right, because you have all right, so acetate here is our common ion, and so again, based on Le Chatelier's principle, by adding a salt here, you're also increasing the concentration of the conjugate base. And so based on this chemical reaction equation, which is in equilibrium, the equilibrium will shift towards the left, right? Favoring the formation of the intact acid here. So in that case, because the reactants are favored, the amount of hydronium ion will decrease because you're shifting it to the left, right? So the lowering of the ion concentration, the hydronium concentration, will result in the increase in the pH, which means that it becomes less acidic. The solution will become less acidic when you add a salt containing a common ion. All right, so let's take a look at this example right here. Calculate the pH of a buffer solution that is 0.100 molar in acetic acid and 0.100 molar in sodium acetate. And then it gives you the Ka value here of the acid, which is 1.8 times 10 to the negative 5. So how would we approach this problem? So the first thing that you want to do here is to write out the chemical reaction equation, right? So you have the acetic acid being ionized in water. And so that basically releases hydronium ion plus the conjugate base. So it looks something like this, right? So you have the acid right here, which is being ionized by water, and that produces hydronium ion and the conjugate base. Okay, and then once you've written the chemical reaction equation, you want to set up your ice table. All right, so let's set up our ice table here. Right, so initially, the concentration of the acetic acid is 0.1. Right, so we're going to ignore water because it's liquid. And then the initial concentration of the hydronium ion would be 0. And for the acetate, it's also 0.100 because of the salt here. So this is the source of the acetate ion. And so you would proceed normally, right? Populate the ice table. So the change will be minus x plus x plus x. And then find the equilibrium concentration as a function of x. All right, and once you've populated the ice table, you want to set up an expression for the Ka. So our Ka here is concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the acid. All right, and this is equivalent to 1.8 times 10 to the negative fifth. All right, so as you can see here, the x's will cancel, right? So this cancels with this. The reason why is because Ka is less than 10 to the negative 3. So you can use this approximation method, right, in which when Ka is less than 10 to the negative 3. All right, so we use that approximation, plug in the numbers here. Ka is 1.8 times 10 to the negative 5, which is equivalent to the concentration of H3O plus. In this case, we have x times the conjugate base divided by the acid, which is 0.100. So you can see that 0.1 will cancel, and that gives us the value of x. So x here is equivalent to 1.8 times 10 to the negative 5, which is basically the concentration of the hydronium ion. Right? And now you can find the pH of the solution by plugging in this value in the equation. pH equals negative log of 1.8 times 10 to the negative 5. And that gives us 4.74. All right. Here's a cleaner version. Populate the ice table. Then set up your Ka expression. Find the value of x. And plug it into the pH equation, which gives us 4.74. All right, so there's actually a shortcut. There's an easier way of finding the pH of a buffer solution. And that is related to the Henderson-Hasselbalch equation. And this equation, derived from the Ka expression, allows us to calculate the pH of any buffer solutions. Okay, so the equation calculates the pH of a buffer from the pKa and initial concentrations of the weak acid and salt of the conjugate base, as long as the X's small approximation is valid. So notice that in this statement it says initial concentrations. Normally, we find when you perform, the ice table, normally we use the concentrations at equilibrium. But if you look at the previous example, the equilibrium concentration is essentially equivalent to the initial concentration because we use the X's small approximation. Right? We use the approximation method, which allowed us to basically drop the X. Right? And so when we drop the X, the equilibrium concentration is the same as the initial concentrations. So the Henderson-Hasselbalch equation is a very good, way to determine the pH of any buffer solutions, and it's a lot easier because you don't have to use the ice table. Okay, you can just plug in values here for pKa and also the concentration of the conjugate base and the concentration of the acids. Okay. So how do we derive the Henderson-Hasselbalch equation? Okay, so again, here's the equation: pH equals pKa plus the log of the ratio between base and the acid. All right, so let's consider this general equation for a weak acid, okay, in which you have HA being ionized in H2O, in water, and that generates hydronium ion and the conjugate base. So we generate the Ka expression here. Ka equals the concentration of the conjugate base times the concentration of the hydronium ion divided by the concentration of the acid. All right, so in order to get the pH equation right here, right, we need to isolate the concentration of the hydronium ion, because we know that pH is equivalent to the negative log of the hydronium concentration. So it's dependent upon the concentration of hydronium. So we need to isolate hydronium ion by itself. So in order to do that, we need to multiply both sides of the equation by HA, right? So we're going to move HA to the left-hand side by multiplication, right? So we're going to multiply HA on both sides. And that basically cancels with the denominator here. And to isolate H3O plus completely, we would have to divide both sides by the conjugate base. Okay, and this conjugate base will cancel, giving you this equation at the bottom. Right, so now we've isolated the concentration of hydronium ion. So now we can take the negative log of both sides, and we get the pKa, right? So negative log of this hydronium ion, right? And we'll do the same thing for the other side, right? Negative log of Ka. Okay, and in mathematics, the log of A times B is equivalent to the log of A plus log of B. So that means that we can separate these two right here. Okay, so in order to do that, we have negative log of Ka plus the log of the ratio here. So at this point, I'm just going to call this acid, and then the one at the bottom, the conjugate base. All right, and this is equivalent to the negative log of the hydronium ion, which is basically pH. All right, and then we're going to distribute the negative sign here. So negative log of Ka is basically pKa, right? And then distribute the negative here, so that would be negative log of the acid, concentration of the acid divided by the base. And that would be equivalent to the pH. So this is another form of the Henderson-Hasselbalch equation. So notice that in this derivation here, the acid is in the numerator. But the other Henderson-Hasselbalch approach, or Henderson-Hasselbalch equation, the base is up top. So you just want to make sure that if you have the base in the numerator, then this is a positive sign. But if you have the acid in the numerator, then you use a negative sign. Okay, so in the formula sheet, if you're going to use a formula sheet, this is what's given. All right, so the pH equals pKa plus the log of base divided by the acid. So it's probably better if you remember this, but if you don't, that's fine. It's going to be given in the formula sheet. So here's a cleaner version. So when would be the best time, or when is the right time to use the Henderson-Hasselbalch equation, right? Because you can use the full equilibrium analysis. You can use the equilibrium approach or the approximation approach to find the pH. So when can we use the Henderson-Hasselbalch equation to minimize the time required to calculate the pH, right? So the Henderson-Hasselbalch equation is good enough when the approximation method is applicable, okay? So that means the Ka value should be small enough, right? So the approximation will work when the initial concentrations of the acid and salt are not very dilute, meaning they're not, they should be concentrated enough in order to be able to perform the analysis, and that the Ka has to be fairly small, right? And so to summarize, the first two bullet points here, the concentration of the initial concentration of the acid and the salt should be at least 100 times greater than the value of the Ka. So for instance, you can have a concentration of the acid equivalent to, let's say, 1 molar, right? Same thing with the salt. So the Ka value has to be at least 100 times less than 1 molar. So we can say 0.001. So if Ka was equivalent to 0.001, then we can use the Henderson-Hasselbalch approach. So that's what this is saying. So let's look at an example. Calculate the pH of a buffer solution that is 0.050 molar benzoic acid and 0.150 molar sodium benzoate. And then you're given the Ka value of the benzoic acid, 6.5 times 10 to the negative 5. Right, so we have here an acid and the conjugate base, right? Salt of the conjugate base. So the benzoate here, C7H5O2 minus, is the conjugate base. All right. So we're going to compare two methods here. Right? The first one is going to be the equilibrium approach, and the second part is going to be the Henderson-Hasselbalch, just for comparison. So let's look at the ice approach first. Right, so we have benzoic acid, so we're going to write the chemical reaction equation for benzoic acid. That's being ionized in water. And so here's our reaction equation, and now we populate our ice table. Okay, so the initial concentration of the acid is 0.05. Initial concentration of the hydronium ion is 0. And then for the sodium benzoate, it's 0.150, right? Coming from this salt. And then the change is minus x plus x plus x. And then you proceed normally. And then you can see that the Ka value here is less than 10 to the negative 3, and so we can just drop the x. All right, and then you generate your Ka expression, which is the concentration of H3O plus times the concentration of the conjugate base divided by the concentration of the acid. All right, so that would be x times 0.150 divided by 0.05. Okay, this is equivalent to the Ka of the acid, which is 6.5 times 10 to the negative 5. Okay, and you work the math out and isolate x by itself. and we get 2.17 times 10 to the negative 5. All right, so this is also equivalent to the concentration of H3O plus, all right, in molarity. All right, and so we can just plug this into the pH equation, negative log of this number. And that gives us a pH of 4.66. All right, so this is the equilibrium approach, right? Or you can just simply use the Henderson-Hasselbalch approach. But first, the condition has to be met, right? And so the condition is that the Ka value has to be 100 times less than the concentrations, okay? So you can see that the concentration of the benzoic acid here is 0.05, and so we know that if you divide 0.05 by the Ka value, it's at least 100 times greater, right? And so yes, we can use the pH, the Henderson-Hasselbalch approach, or the equation for it. So pH equals pKa plus the log of the conjugate base divided by the acid. All right, and we're given the Ka value here, so we just take the negative log of that value plus the log of the conjugate base. Concentration is 0.15 divided by the concentration of the acid, which is 0.05. And this gives us a pH equivalent to 4.66, which is the same as the equilibrium approach. So here's a cleaner approach. So again, using the equilibrium approach, we populate the ice table, find the Ka expression and the value of X, plug it into the pH equation, we get 4.66. Or you can just use the Henderson-Hasselbalch approach. Using this equation, and we get the same pH, which is 4.66. All right, so that's it for today, and we're going to continue this in part 2.